we're looking at problem 2a. It starts out, use Stokes Theorem to evaluate a line integral. The line integral they want is the line integral around C, where the vector field is minus yi plus x squared j plus z cubed k. C, the curve, is the intersection of the cylinder x squared plus y squared equals 4 and the plane x plus z equals 3. And the curve is oriented so that it's traversed counterclockwise when viewed from above. Well, let's take a look at what we're looking at first. So here's the line integral they want. Here is the vector field that we're given. They gave us x squared plus y squared equals 4, which we can draw without killing ourselves at all. We can then take the intersection of that with x plus z equals 3. I'm going to rewrite this as z equals 3 minus x. Now if this is x and this is z and this is y, that plane is going to come down at a slant like this. That's all I really care about. And we don't need a great picture to do these. I do want that curve, because it's a circle above here, traverse counterclockwise when looked from above. What that should mean is that when I look at the shadow of this down in the xy plane, I'm going our ordinary counterclockwise, which is great. Now, they did say evaluate this line integral, but they didn't say evaluate this line integral. They said use Stokes Theorem to evaluate this line integral. So I'm not going to start out with parametric equations. I'm supposed to look at the right-hand side of Stokes Theorem and start working all of that out. So just a reminder of what the right-hand side of Stokes Theorem looks like. It looks like a double integral. We have the surface S. We know that's going to be our little disk that's being cut in a slant. We're supposed to have the curl, which we will calculate. We have to dot that with the area vector. That's not going to be a complicated area vector, which is great. And then we're supposed to do this double integral. So we're not going to evaluate this with parametric equations or Green's theorem or anything such thing. We are going to be doing the right-hand side instead. So first, let's calculate the curl. Calculating the curl. I know this is a cross product. We know how to calculate cross product. We want to put I here and j here and k here. We want the del operator as the second vector. So it's the partial with respect to x of, the partial with respect to y of, the partial with respect to z of. And then I want minus y x squared z cubed, like that. And let's try to make sure we calculate this right. I'm supposed to cross off the I row, cross off the I column. I'm going to get the partial with respect to y of z cubed, which has no y cubed and no y in it at all, that's 0, minus the partial with respect to z of x squared. So our first entry is 0. All right, then I cross off the j row, cross off the j column, put a minus, because that's what we're supposed to do, right? Plus, minus, plus. And what am I going to get? I'm going to get the partial with respect to x of z cubed, again that's 0, minus the partial of with respect to z of minus y, that's again 0. I don't care about that being minus anymore. Now for the last one, I cross off the k row, I cross off the k column and just see what's left. I'm finally getting something. I get the partial with respect to x of x squared, that's 2x, and then minus the partial with respect to y of minus y, that's minus 1. So our curl vector is just the vector 0, 0, 2x plus 1. All right, I'm going to erase my calculation. You can go back and see it if you like. Better yet, you should do it yourself. Not a hard calculation, and it's good to be in the habit of it. So I'm going to get integral s, and then I'm going to get the curl vector 0, 0, 2x plus 1. Yay. Dot it with our area vector. Well, we now need our area vector. The only way we know how to find area vectors this semester is if we're lucky enough to have a function. If z can be written as a function of x and y, well, we have that. We just have 3 minus x. And just a reminder that the area function should then be minus fx minus fy, 1 like that. And in this case, it's very simple. I should just get 1 and 0 and 1. So that's actually our area vector. We should have dx dy to make sure it's an area. All right, so I put that over here like this. I go 1, 0, 1. This is going to be dx dy. And when I dot those two vectors, I'm still going to get integral, integral. I'm just going to get 2x plus 1 dx dy. However, S is still that circular chop that's going like this up in space, and we're only allowed to actually use x's and y's. So what we need to do is look at the smooshing of that down to the xy plane. And we knew we were hitting x squared plus y squared equals 4, so we know the shadow is just going to be that disk in the xy plane of radius 2. Now that being said, I think polar is going to be a better option than anything else, so I'm going to go polar. I'm going to go like this. Instead of 2x, I'm going to have 2r cosine theta plus 1. We know that instead of using dx dy, we need to use r dr d theta. And I'm not saying dx dy equals r dr d theta. We know this. These french fries are different than the shape of these french fries. In order to find the limits of integration, we're supposed to draw rays, but every time I draw a ray here, the rays enter the region when r is 0. The rays leave the region when r is 2. And then I have to go all the way around and drawing all those rays. So that's the integral I get to do. I don't think that's a terrible integral, but let's work our way back up the page and work out the integral. And hopefully we're not making any mistakes along the way. Now in order to do this, I need to distribute the r first. So this is going to be 0 to 2 pi. This is going to be 0 to 2. This is going to be 2r squared plus r. Let's put that in the cosine theta. Cosine theta plus r. I want 2r squared plus r. Yep. Dr d theta. We already put the r in. So now we take the antiderivative with respect to r, and I'm going to get something like 2/3 r cubed. That's going to be from 0 to 2 times cosine theta plus 1/2 r squared from 0 to 2. This is all going to be d theta. So I get the integral from 0 to 2 pi. Let's see here, that's going to be what looks like 8/3 cosine theta. When I put in the 0 into the r cubed, I just get 0, so I don't have to worry about that. When I put in the 2 I squared, I get 4, and this should just be plus 2. Like that. And what we need to do is just finish that integral. All right, here we go. Antiderivative of 8/3 cosine theta is 8/3 sine theta, like this. And the antiderivative of 2 is just 2 theta. And I want to go from 0 to 2 pi. Let's try to leave as much as we can here. Now when I plug in 2 pi into sine theta, I get 0. When I plug into 2 pi into theta, I should get 4, so I get 4 pi. When I plug 0 into sine theta, I get 0. When I plug 0 into 2 theta, I get 0. So we're getting a final answer of 4 pi. Seems a very popular answer for these kinds of problems.